everyone, and welcome back to PlutoCon 2021. I think it's going great. We had a good day yesterday with lots of interesting talks. I want to take a second to thank Julia Computing for giving us this YouTube channel to stream on. And also they're the ones hosting all of your demo notebooks right in your browser. Okay, so lots of talks today. The first one will be by David Sanders. We work together on the MIT course, so that's computationalthinking.mit.edu. And okay, over to you, David.
Well, thanks so much, Fons, for the invitation. And of course, thanks for creating Pluto. It's amazing. And thanks for setting up this great conference, which is going very well. I'm really enjoying the talks. So I'd like to talk about this course that Fons just mentioned. So what it is an interactive online course about computational thinking. Basically, how can we use the computer to do stuff, to do applied mathematics, to do computer science, to do scientific computing. And okay. There we go. So what we're trying to do is actually make classes come alive. And by live, I mean using some kind of live interactive notebook experience, right? Some kind of interactive ability to manipulate, work with our computations in a much more interactive and interactive way in order to enhance learning, basically. But it's not just about a course, actually. I also use Pluto for my research. Many people do. And so in general, it's just for interactive computational thinking. And we're making computation come alive. Computation in all its glory. Okay. So the point is that we believe strongly that computation enhances learning. I like this quote from Alan: "You only understand a concept once you can actually compute with that concept in Julia, and in particular in Pluto, so that we can then not only compute with it, but make it interactive." And I'm going to show some examples of that. Okay, so we really have this belief that interactivity enhances understanding, and visualization also enhances understanding and computation in general. And I, in particular, I'm a very visual person, and I strongly believe that if I had had all of these tools available when I was learning these subjects, basic subjects, even like linear algebra, probability, sort of basic mathematical concepts, I believe that I would have actually gained a lot more understanding a lot faster, just by playing around with the objects, visualizing them, seeing how they behave. Okay, so what is this computational thinking course? Here's the link to the website. It's joint work with Alan and Fonzie. And so we have an online interactive textbook that Alan actually was showing us today, and so which are made up of Pluto notebooks. Then we have live lectures where we use Pluto notebooks as well. The same Pluto notebooks, really, but they don't necessarily need to be the same. And often what we do is have some Pluto notebook set up, which is kind of the online textbook, and we're working through that during a live lecture. But then we, in the moment, we start doing some live coding when an interesting question comes up. And I think, I love doing live coding. I think it's really important to actually show people how live coding works and how you think about a problem. And, oh, I just came across, a mistake. Let's fix it. So I'll show an example of that later. And we also have live homework that Fons is going to talk about in a bit. And that's also Pluto Notebook. So Pluto is really the enabling technology for the whole course. And I believe that any computational course in particular can really benefit from Pluto. And it's, to some extent, an open question to what extent non-computational, sort of more theoretical courses could benefit. But of course, it's also our belief that, and that's part of the point, is that any sort of, quote, traditional non-computational course can actually be greatly enhanced by having a computational component with all this interactive work. So why interactivity? So this is just a sort of list of a few of the tools that I've ended up using during my kind of PhD and then career. And so, starting off with C and GNU plot, I actually did some interactive programming with OpenGL. And for 3D visualizations, that's still almost state of the art. Now we have Mackie in Julia, which basically gives us a really nice interface for that. And so my sort of stretch future goal for Pluto is that and it doesn't seem to be that far away, is that really we want to be able to incorporate WebGL Mackie to have interactive 3D plots inside Pluto. And a revelation for me was when in 2013 or 12, I attended a SciPy conference where they announced the IPython notebook. This was just really a revelation that you could actually have one computational document that included all of your different kinds of activities. Of course, this was based on the Mathematica notebook, and so it's not a new idea, but the idea that everything was open source and you could really just share these with anybody and anybody could run them. And then fast forward a few years, then we have Julia, and then interact.jl enabled you to do interactive things with Julia inside the notebook, but it was unfortunately never, it sometimes worked well, and then it just stopped working and it was difficult to fix. And so Pluto really, when I saw Pluto for the first time, a year ago, I just thought, well, this seems to be solving a lot of issues that we've been having. And I think it's really, Fonzo's done a beautiful job of making it into a really nice tool for, as I said, for exploring computation. Okay, so here's a couple of interactive kind of demos that we might want to be able to use. So here's one called Mathlets, which comes out of MIT. So it's pretty, it's really nice kind of Java applet or something. You can click here and you get new trajectories, and you can move this around, and this phase portrait of a differential equation moves around. Fantastic. Now, what about nonlinear equations, right? This is a linear equation, linear ODE. What about nonlinear ODEs? Where do I find that? Oh, it's not there. Okay, well, let me modify it to make this linear equation into a nonlinear one. I look again, and I can't find that either. I have no idea how to modify this. In fact, I believe that the source code is not actually available online. So now I have to get back to my, how do I get back? I should not have clicked that link. Oh dear. This is the problem of live demos.
Uh-oh, maybe you can refresh.
Classic.
Classic.
Oh dear, that's the wrong one. Never do live demos and talks. I've learned this so many times, and yet here I am. What's going on? There we go.
Oh, awesome.
Okay, sorry about that. So, then probably many people know Desmos.com, which is a really beautiful graphing package. Hold on. Sorry, I lost now a really beautiful graphing package. So where you can do things like this. You just type in a times x squared plus b times y squared equals 1. It suggests to add these sliders. I'm just going to add all of those sliders, and then I can set those running, and we see this curve moving around. So that is what I would like to be able to do. And again, this is just a beautifully executed website, and lots of people use it from sort of, I don't know, K through 12 up to university level to graph things. But again, I really want to know, well, how are they actually drawing these contours? And how come it's so fast? How come it's so smooth? And of course, this is a commercial company, so they don't have the source code available. I can't find that out. So here's another example: is interactive linear algebra textbook. Very nice textbook. Here's an example. You have these points. You're fitting an ellipse to these points, and then let me just zoom in a bit. I can actually drag these points around, and this is it tells me what the best fit is. It's fantastic. But then you look at the source code, and it's kind of disgusting JavaScript or something that I really you can't see what's going on because they're mixing up the maths with the visualization, and it's written in the wrong language. Okay, so that Pluto is trying to solve all of these problems. So yeah, as I said, where's the source code? I want to learn how to be able to do that myself and how to modify their examples. And so, but in an easy way. And this is what I've been actually searching for a very long time. And Pluto provides, a really nice environment to be able to do this. So I'd like to actually show an example notebook that I made for this conference that unfortunately currently is not working in the online version. So I'm just going to show that quickly. So this is about plotting inequalities. So what, like x plus y is less than 1. And it's using these methods that I've been working on called interval methods. I won't really go into that. So what we're going to do is, well, we can select an expression. And when we select this expression, this drop down, you can actually pass through. Now this is not working either. Is it working? Okay. You can actually pass through this. You pass through the string from this drop down to this text box, and now I can actually modify the text box. And then I'm going to actually draw the set that satisfies this inequality. So blue is what's inside, orange is what's on the boundary, and white is outside the set. Right? So I'm inputting a string here, and then just like Nick showed in his beautiful talk yesterday, I'm evaluating this string. And x and y here are actually symbolic variables from this symbolics.jl package. So x is a symbolic variable x, and x plus y actually gives me a symbolic expression x plus y. So I'm using that, and here's the symbolic expression once I've substituted in the numerical values of these parameters a, b, etc. Here's the symbolic expression, and then I'm using my interval methods to actually plot it. So basically what interval methods can do is you put in a box like this square, and it will evaluate this function over all points simultaneously in that box. And it'll give you a sort of overestimate of the range. And so you can actually basically calculate for all points in this box, is this inequality satisfied or not? If it is, then we'll color it blue. And actually, what we're doing is this. If I click the show boxes, you can actually see that I'm splitting up space and sort of repeatedly bisecting space to cover space so that I can, for example, this huge box, I proved all at once that it was inside, using interval arithmetic, that it was inside this set. But then as I get closer to this boundary, I have to actually subdivide more and more. Okay, so then I can choose more interesting expressions like nonlinear expressions. And here's a nonlinear expression, and then I get something like this. And let's get rid of the legend. And now I can actually start moving. The amazing, beautiful thing about Pluto is that now I can just start moving these sliders around, and everything updates automatically. So what I'm doing is updating this symbolic expression and then converting that into an actual algorithm, right? So this is a declarative version of a constraint. It's saying, I want to constrain my variables x and y by this function. And then I'm actually converting that into an algorithm that calculates whether that does something clever, which is basically, just scroll down a bit, which is this. Given an input box, I'm actually contracting it into different pieces. So one piece is the stuff, this inner thing is everything that I have proved that is inside the set, the set of interest, which in this case is a circle, this disk. So this is, well, this orange is actually completely inside the disk, the green is outside the disk, and this purple is on the boundary where I don't know if it's inside or outside. And so the point is I'm actually able to throw away this green piece because I don't want the stuff that's outside the constraint set. So that's what I'm doing. And in order to do that, I have to generate this algorithm called the forward-backward contractor, which is a linear sequence of steps using interval arithmetic to remove pieces that don't satisfy this. And that's what I'm doing under the hood. But all of this is happening automatically. So I'm generating this code from this symbolic expression at every time the slider moves. And the amazing thing is it's all sufficiently fast to just do it almost interactively. And there are some very beautiful ones you can play around with. So like this is a great example from a paper by Tupper. And so this is his original expression, but now we have Pluto. I can just change these things around by adding in my parameters. And I get something completely different that maybe nobody's ever drawn before. And now when I move these parameters around, it redraws the constraint set. Okay, that's probably enough. So this is a pretty good example, though, of how you can define, how you can sort of define an interactive user interface for your users. And this is going to go online, and then they can play with the sliders. And what did I want to do? I wanted, initially I was just going to have this drop down, and then I thought, well, but but then I'm actually restricting what the user can do, right? The user probably wants to say, oh, I don't want that exact expression. I want to be able to modify that expression. And so that's why I added this text box, because I was constantly searching for how I could give the user more interactivity, compared to that MIT Mathlet's applet, where I can't modify anything. Here, at least, I can choose. They could also have a drop down, of course. This drop down idea is 20 years old or more. And then actually being able to modify it yourself is, of course, a goal that many people have had for a long time, and now it's relatively easy to do that. But still, I'm missing the user having more control, right? So I even added another slider because I wanted to be able to control the size of the input box. But in the end, all of this is basically I, as the author, am having to add more stuff because the user does not actually have access to the source code. If the user had access to the source code, they could literally change this themselves or add a slider themselves. And that's the point of Pluto. Okay, so let me go back to my talk. So what are the key enabling technologies in Pluto? I mean, everybody probably knows this. I mean, we have seamless interactivity by turning any variable into a slider, and I'll show that in a minute. And then text is also just Julia code, and so it can also be interactive. And we have this presentation mode that I'm using, right? This is actually Pluto. If you wonder where there is a presentation mode built into Pluto. And so basically the user has sort of total control, or a very large amount of control of what happens in their notebook. And they can do very cool, interesting things. More so than Jupyter or IPython, as it used to be called, that I used to use. You have more control in Pluto. You can do more interesting things. And so there are some tensions, though, when teaching with notebooks. So I just, as I said, I just had this interactive demo that I built. But on the other hand, I also want to do live coding. And so actually what I want to show people is really how they can build their own demo, right? It's more fun to build your own interactive UI than see somebody else use one. But we also want to be able to do live coding to show people how to think computational. And then a teacher would want to highlight particular examples that they think show something off very well. But then, I always want to be able to change those examples and like tweak them, move the parameters a bit. So, actually nowadays when I read a book or a PDF and there's a figure, the first thing I always think is, oh, I really want to be able to manipulate that figure. I want to drag points from the figure and see what happens, just like that interactive linear algebra example I showed. That's a great example. But again, I want to have control as a user. I don't want to just be restricted by what somebody imposed. Okay, because by doing so, you actually exclude exploration, which is one of the joys of having a computer available, is that you can just explore what happens. So there's this great book, Exploring ODEs, by Nick Trebethan and some other people that I've temporarily forgotten, where they use ChebFun in MATLAB to explore ODEs numerically, and we should just have that all in Pluto notebooks in Julia, and you would have sort of a great way to very quickly understand ordinary differential equations and what they're capable of. Okay, so I thought I would do an interactive live coding session, but I've actually used up a lot of time already. Fons, what do you want to do?
Yeah, I think maybe I should show the homework and they can see the live coding session at our JuliaCon presentation, or I guess at the computational thinking course.
Yeah.
So what we wanted to show was how we teach using notebooks on the course, or how David teaches on the course. So you can go to computationalthinking.mit.edu to see a sample. So one thing we do is live lectures. The other thing we do is notebooks on the website, and they work on the website with sliders and buttons. And then the last thing is we do homeworks also in Pluto. And so the homeworks look a bit like this. So this would be homework 5 from the last semester. These are available online. So if you're interested, you should download them and try them out for yourself. Even if you already know how random walks work, I recommend, if you're a teacher, to try out one of the homeworks and see for yourself what the student experience is like. It's very different from what you've seen before. So So the goal of our homework is always to have a narrative. So we try to get somewhere and we build up the structure, like the Julia code structure slowly, and we have them involved in every step of the process. So something we have very commonly is we define a struct, and then we ask them to do something with that data type. So this would be a homework about random blocks in 2D. And then we define the struct coordinates, and just to get them used to structs in Julia and our data type, we ask them to construct a coordinate located at the origin. So I already have this cell. So this would be what it looks like when the student opens the homework. And so it starts out with origin equals missing, and it says, here we go, replace missing with your answer. So you say like, I don't know. And now it's going to give me an error. And it says, oopsie, make sure that you define a variable called origin. Okay, so I guess let's start with coordinates. It says make sure that origin is a coordinate. Okay, this one is actually maybe a bit confusing. So I don't know, let's try this. This will give me an error. And that's fine. So eventually, for example, I could try a tuple. It says make sure it's a coordinate. And eventually, hopefully, they get to this point, and now they know how to construct the coordinates. So how did this work? Let me show the code, but like don't be intimidated. So what you see is it's just a series of if-else blocks. So the first one is we check if it's not defined, and then we show the not defined warning. Let me show what this is. So it's just a function, you give it a name, and it will show the red bubble. And you can take these functions from our homework, they're at the bottom, and you can use them in your course. So if it's not defined, then we show this, and otherwise I have a let block. And so here it's just a series of if, else, if, else, if, else, if, else blocks. So first we check if it's still missing, because that's how we start out all of our exercises. We don't want an intimidating error when you start at the exercise. We just say like, here we go. Then we check the type. And then finally, if we know the type is correct, we check whether it is actually at the origin. So yeah, one like this, I just copy and paste, and when there's a similar exercise, I reuse it. So this was a very simple exercise, and let me go on. So for each exercise, especially if it's very crucial that they get this one right for the structure of the homework to work, we do pretty detailed checks. And then finally, so we build up, we have an array of possible moves because we're looking at a random walk in 2D. So that would be to the right, up, left, down. And then we have a small exercise to get them familiar with having a list of moves. And then they have to write the trajectory function. And so we start out with, we always have a template or like placeholder function, which has the right inputs and the right types so that the students know what types they're going to get. And it returns missing, and they have to write their code like inside this function body. So it starts out just here we go, and then they'll work on this, and I will just go straight to the final solution. So one thing we do is we do three things for a big exercise like this one. First, we just apply their function to some basic test case without anything extra, so that they can clearly see what their function is returning and whether it looks correct. Then, like if I have the time, we add a cool visualization. So in this case, we plot the lines for their trajectory. You can rerun the cell and get like funky new trajectories. And then finally, we have a check. And so for this check, I tried not to put the solution in here because students can view it. That's a subject for another time. But what I did essentially was I count whether the number of unique positions, so the length of the set of the positions after doing 100 steps, if that's less than 90. So then like I'm guessing that it was random because it crossed its own path sometimes. And you can give hints based on what's happening. So if the number of unique steps is too high, then probably it wasn't random. So we say, are you sure that you chose each step randomly? I think the most important thing is, don't you say correct wrong, because it can be difficult to, like, if it's wrong, then you need to know why, because there's nothing to debug if it's just saying that it's wrong. So try to be specific. Yeah, I think you should try this out for like a small exercise and see how it goes. I have a couple of tips. So this is more general. If you're publishing your homework, a self-contained homework file works best. So that means use a PKG cell. So that means in your notebook, do all the PKG operations you need to get the packages there, so that students don't need to install packages. And I will talk more about this at a later talk. Second one is put your data online. If you're using data, just get it somewhere on GitHub and then download that data into your notebook. That way students don't need to download the whole folder, they just get that one notebook file. And finally, if you have helper codes, just put it straight into the notebook, and then it's still a single notebook file. So yeah, I recommend having a go at one of these homeworks, trying to just do the solutions yourself and see how these checks are implemented. And yeah, hopefully you can use this to make your homework more interactive. Kind of one of the ideas was, since it's a Corona semester, students don't get the person-to-person feedback, and so now the homework is kind of giving that feedback. You can also see it as instead of your TA working on answering questions, they could work on writing these checks directly into the homework so that you answer those questions before they even come up. Also note the big difference between doing this, live checks while you write the questions, and auto-grading homework. Because when you auto-grade homework, it can be very frustrating. I don't think any students likes their homework to be auto-graded rather than manually graded, because you have things like they expected a floating point, but you round it to an integer and then it's incorrect. And you don't have these types of problems when you have live checks. Okay, that was it. Thanks. And check out the course, Computational Thinking.
Yay. So thanks for this. And for a few questions which came up. So Panagiotis, maybe you want to start?
Yeah, so people at YouTube ask, where are these homework available online? Can they see it? And another question was, how do you make slides with Pluto?
Let me answer the first one. So it's computationalthinking.mit.edu. And I think you can also Google for Computational Thinking MIT. And you go to the spring semester, and there you can see the homework. And all of the homework so far, you can just click and view them right in your browser. But I recommend downloading them, running them, and trying it out for yourself. It's really cool. It's really different than something you've seen before. Presentation mode is built into Pluto. You can Google for presentation mode Pluto, I think. I'm pretty sure.
Awesome.
I can quickly show my notebook.
Right. Yeah. Sorry.
So basically, it's just like a normal Pluto notebook. I just have markdown cells, or markdown in a cell, and you just use these different levels of hashes for different levels of headings, and Pluto will actually interpret all of that as a slide once you're in the presentation mode. And to get into presentation mode, you use this little clever piece of JavaScript. So you need this JavaScript present function. You can wrap that in an HTML piece of code inside Julia, and that'll give you this present button. So when I click the present button, I'm now not in presentation mode, and then when I click it again, I go into presentation mode, and it gives me these arrows, and then I just you're just paging through the same notebook. It just adds a lot of white space to make it the right size for a page full of slides. So if I just scroll down, you can see that the slides are actually just one after another, but these arrows are just sort of moving to the right location in this long HTML document. It's very, very nice design, very clever.
It's surprisingly effective.
Yeah. Surprisingly easy, surprisingly useful. Yeah.
Okay, thank you, David.
Thanks.
I think we should go on to the next talk, which is by me. It's a talk by me about how to use JavaScript inside Pluto. All right, thanks. See you there.